Suppose now we have a transition between impedances. So from impedance Z1, the string is attached to a different piece of string with impedance Z2. So the impedance changes across this boundary at x equals to d. Now we could equivalently take away this string with impedance Z2 and have a damper with impedance Z2, and this string here can't tell the difference. So we'll think about this case first. Now in this case we've got to consider the possibility of a reflected wave. So in this region here we're going to write the wave as the sum of incident and reflected waves like this, and the incident wave is going in the positive direction because of this negative sign here, and the reflected wave is going in the negative direction because we've got a plus sign here. Now the vertical force on the string attached to the damper here, so the string attached here on the left of the damper, the vertical force will be given by the sum of the gradient due to the incident and reflected waves multiplied by the tension. So you want the vertical component of the force, it's the tension multiplied by the gradients. So that's this term here, the tension multiplied by the gradient due to the incident and reflected waves. We can rewrite that in terms of the impedance and the velocity, the vertical velocity of the incident and reflected waves, like this. Now, the change in sign here comes due to the different sign here inside the kx minus omega t and the kx plus omega t. This plus sign leads to a sign flip here comparing the incident and reflected waves. So now at x equal to d, the velocity of the string is given by the sum of the velocities yi and yr, so yi dot and yr dot. So the applied force by the damper is given by the product of the impedance of the damper, Z2, and the total velocity of the string at that point. So this is the force applied by the damper. But we know that the force applied by the damper must be equal to the force in the string. So that means this part here, proportional to Z1, must be equal to this part here, proportional to Z2. Rearranging, we can find the velocity of the reflected wave is equal to this fraction given with the impedances multiplied by the velocity of the incident wave, and integrating, we find that the reflected wave amplitude is given by some ratio of the impedances multiplied by the incident wave amplitude. And this is the relationship between the incident and reflected waves at this boundary, which is represented by a damper, but we could equally represent it by a continuing string with impedance Z2. Like this. So now we have the reflected wave amplitude given by this. We can rewrite this as the reflected wave amplitude given by r times the incident wave amplitude, where r is this ratio here. Now suppose we want to consider the transmitted wave, so the wave that goes to this boundary and then gets transmitted into a string with impedance Z2. At the boundary, we must have the amplitude of the transmitted wave is equal to the sum of the amplitudes of the incident and reflected waves, so that the string is continuous across this boundary. Therefore, the transmitted wave amplitude must be equal to the incident wave amplitude plus r times the incident wave amplitude, or 1 plus r times yi, which is given by this. So, in summary, we have the reflected wave amplitude is given by this, where r is some ratio of the impedances, and the transmitted wave amplitude is given by t times yi, where t is 1 plus r and equal to this. For the case of a transition between strings of different density but constant tension, the impedance, Zj, is given by t divided by Cj, where c is the phase velocity of the waves on the string. So we can rewrite r as some ratio of the velocities, and t as some ratio of the velocities as well. Let's look at an example now where we have a string with constant tension, but the density changes. So when the density changes, we have the impedance being proportional to the square root of the density, and the velocity proportional to the inverse square root of the density. So changing the density changes z and c, but in an inverse sort of way. And this is the reason when you look at the reflection coefficient, for impedance you have z1 minus z2, but for velocity you have c2 minus c1. So these equations look kind of the same, like you could just replace the z's and the c's, but you can't. You've got to be careful. And similarly here with the transmission coefficient. Let's look at an example first where we go from a region of high velocity to low velocity. So that is low impedance to high impedance. So wave propagates along quickly. When you cross the boundary, it slows down and compresses. And on reflection, we have an inversion in the phase. So on transmission, the compression is when you reduce the velocity. This is a Snell's law effect. You may remember Snell's law from optics. When you go from a region of high velocity to low velocity, the wavelengths get shorter. So here, the whole wave has got shorter. On reflection, the phase is inverted, and you can see this in the reflection coefficient, which is negative when you have Z1 minus Z2 being negative, or C2 minus C1 being negative, which is the case here. The transmission coefficient is some number less than 1 because R is negative. And so the height of the wave on transmission, you can see the amplitude is lower than the incident wave. Okay, let's go now for the example where we're going from a region of low velocity to high velocity. That is a region of high impedance to low impedance. So the wave propagates along fairly slowly, and then it speeds up and reflects. On reflection, we have no phase change, and on transmission, the wave gets bigger. So we look at the reflection first. Well, now the reflection coefficient is positive because the sign of this top bit here is positive. It also means the transmission coefficient is a number larger than 1. So that's why the wave gets bigger as you go across the boundary. Now you may wonder whether this has some implications for conservation of energy, but remember on this side the density was higher. So for a given amplitude of wave, you've got more energy on this side than you do on this side because of the change in density. So actually the conservation of energy, of course, works out.